So now, why do we need Dirac delta functions? We need Dirac delta functions because they're a convenient way of stating determinism. And what do we mean by that? In deterministic dynamics, we mean that if I have a unique starting point, it has unique trajectory. So after a time t, I'm at a unique place. And the way to state that is to say that if I start someplace, let's call this x0, and I have my law of motion. Let's remember that we are studying, at least in this part of the course. I'll get to stochastic systems at some point, but right now we're studying places where we have space M and law of motion. And the law of motion says I move around, and at time ft of x0, which I might call x of t, I'm in one place and one place only. So Dirac delta function is a good way of saying this. Let's say I start someplace. Where do I land? I land at a point y, and that's a unique point, meaning this function will be 0 unless y is exactly on the trajectory time t late. So that we'll find very convenient to reformulate dynamics and describe evolution of densities. So, it says this is unique. And we'll give this a name, various names. So this one we'll call lambda for no good reason. You start at point x, and then there's a parameter of evolution. I'll put it here. For not very string reasons. And in deterministic dynamics, in general, in quantum mechanics and stochastic processes, this is called a Green's function, or says if I start someplace, what's likelihood I get someplace else. In determinism, the likelihood is very sharp. I don't get any place except one point, and that is conveniently formulated by delta function. Now, if you don't like Dirac delta functions, it's fine with me, but it's just a very convenient way of bookkeeping how dynamics works.